Okay, good morning, everyone. Now let's come to the last session. Okay, we have two more speakers. Okay, the first one will talk about parallel entry search, and the second one will talk about endgame for backend games. So let's welcome the first speaker. Okay, Yokoyama. Okay.
Thank you very much for introducing. I'd like to talk about a new parallelization method of chess game research. Nowadays, main process in many computer chess is game tree searching. To make strong player, we want to search the game tree deeply and widely during giving thinking time. However, performance of single computer is very limited. Then it is effective that using many computers and search in parallel. Now, we focus on the low cost and slow network. For example, home use Ethernet LAN. It is very easy to prepare the huge cluster, but in such environment, it is hard to frequently share the alphabet window and the transposition table. So existing parallelizing method, TDS-AB or AFIT, are probably not suitable for this environment. On the other hand, GPS Shogi has a successful case. And GPS Shogi is a shogi program for a low-cost environment developed by our team. In 2013, GPS Shogi participated in a commercial match against human players and defeated a professional player, Mr. Miura, 8th downgrade. For this match, 679 iMarks in seminar room cooperated. See this photo. There were many reporters and photographers, but the computer of GPS Shogi didn't become nervous and didn't his best performance. However, GPS Shogi has some problem. It needs a hand adjustment. It is boring and makes difficult to apply to the other games. Then we propose a new method without hand adjustment. This method can construct the distributed system from single machine program and expert game record. These two sources to our method and output can construct distributing such a system. And we called GPS Shogi's parallelization method GPP as game position parallelization. First, I'll introduce about GPP. GPP is a master-worker system. They are doing communication with TCP, and a master works as TCP server. These clients are doing existing shared memory parallelization search. And this figure is an overview of GPP. It shows a chess game tree, the same of my proceedings figure 1. Then shallower part drawn by the blue line. This is maintained by the master. We call this part master tree. And worker is assigned to the deeper part of the game tree. Each worker seems to be a leaf of the master tree. We keep count of leaves equal count of workers. Each worker searches independently only in such assigned part. For example, worker A is only following NF6 part, and worker B E6 part, and each independently. Now, short as others leaf are corresponding to multiple positions. All sibling positions expect already having workers. This is there is others worker, and this is assigned to except NH6 and E6 other siblings. And this is the structure of GPP. Then, what communication do they have? Communication in GPP method is small and low frequency. Before thinking of every term, the master constructs the master tree and gives orders to each worker and which position should be starting point. And while searching, workers periodically report their search result. While searching, workers reporting to master of his search result. The master collects these reports and refreshes of the master tree. Master receives a worker's report and refreshes his master tree. When the program or the opponent plays, the master tree must be reconstructed. A root position of the master tree is following up the board situation. Now this is an old current position, and if this is played, if this position played, a new root position is this. Now, first, unreachable positions in the master trees are discarded, and assigned workers are freed and pulled for waiting for next assignment. These workers are to be unreachable and discarded and worker pulled. Next, we expand the master tree and assign pulled workers to new leaves. These are new assigned leaves and newly growth leaves to be assigned pulled worker. In this operation, you can notice that red circled workers are not changed their assignment. These workers can continue search without interruption. These workers continue searching without not changing their assignment. Now we reviewed about GPS shorting and GPP. Then I'd like to talk about our new method. In short, our method is about master tree growing strategy. In GPS shogi, it is based on some heuristic parameters and adjustment by hand. This is programmed to apply to chess and the other games. Then we introduced an optimization probability model. This model can evaluate the master tree's utility, and the model was made from parameter-free approach, and then we can easily apply to chess game. Please see this figure that I showed earlier. Blue circled workers are discarded when growing a master tree. The search result of these blue circled workers, result of are unusable anymore. These can be seen as search overhead. Our goal is reducing these discarded workers. In other words, red circle workers which search same position for a long time want to be increased. We made a model to evaluate the master tree based on this goal setting. in our model, we introduced the idea of the realization probability proposed by Tetsuro. For example, this left tree, this tree has two leaves named A and others. Position A has realization probability 0.55, means position A is placed 55%, and other than A position is placed 45%. Now, the future position must reach exactly one leaf, so the summation of the probability is 1. Summation is 1, and this tree summation 1. Estimation method of individual value will be described later. This figure shows change of the probability while expanding the tree. You can imagine a leaf division. There are two types of growing, deepen and widen. Deepen growing is dividing one leaf to two leaves. One is specific position named alpha, and another is other's leaf. On the other hand, widen growing is cutting off one sibling leaf from other's leaf, and then this other's leaf cutting to two leaves. One is B and others. In these operations, the summation of the realization probability is not changed. In this 0.55 to divide two leaves, but summation of probability is still 0.55. Now, I talk about the estimation method of the realization probability. In this research, we use the product of the empirical transposition probability. The transposition probability is the statistical result of a pre-experiment. This pre-experiment uses expert players' record and takes the statistics which runs the worker program evaluate the expert move. To calculate the realization probability, taking the product of these transposition probability value along the rank in the siblings of the master tree. For example, in this yellow circle leaf, the yellow circle leaf is the situation first doing best move and next second best. Then P1 times P2 is this leaf's realization probability. Using this idea, we can measure of master tree's utility. This utility score defined as the summation of the leaf depth weighted. This utility score defined as the summation of the leaf depth weighted by its realization probability. This value is the expectation value of the time period that the tree cares of the real both situation. Note, because of the other leaf aggregate multiple siblings, then we assume the depth of other leaf as a one level shallower. And we are expanding the master tree as maximizing this utility score. This figure shows calculation of the score on the tree growth. And remarks that the increase of the score equals to the realization probability of newly created leaf. For example, this deepen operation. Newly created leaf is alpha and has 0.35, and summation is also increased 0.35. Using this nature, the utility maximization problem can be achieved by the greedy algorithm. Now, show an example of the behavior. In this way, there are four candidates. There are four candidates to be expanded, A, B, C, D. Then calculate the realization probability for each candidate. And calculation result is this. If candidate A has biggest probability, we added A to the master tree. And repeat this operation until all pooled workers are assigned. Using this algorithm, we can know about the tree growth, about expand from where, and how many children it can be known. But we need to decide which position must be added as children. It's also neat. In GPSOT, this is done by 1 second preliminary search. But in our program, we using workers transposition table. We assume that the position such debris are important. Then the information of debit search position extracted from the transposition table and send it to the master. This information is very small, so negative effect to performance should be limited.
Excuse me, please watch time.
Hi.
The times will be paused. Okay, go ahead, no problem. Just watch it.
Now I'll talk about experiments. To evaluate our method's performance improvement, we implemented a chess program and did self-play experiments. The master program accepts UCI protocol, Universal Chess Interface. So many existing chess programs can connect to the server without major alternation. Then we use Stockfish as client, which is one of the strongest chess programs with some changes. Clients run on an equivalent CPU core as single thread. Game opponent is same to one worker. Then time control was fixed to 1000 milliseconds per play. To simulate the communication overhead, we gave syncing time penalty to our program, 50 milliseconds. We believe that this penalty is more than sufficient for overhead by some simple examination. Our workers each play 950 milliseconds, but opponent is 1000 milliseconds. Difference 50 milliseconds is the time penalty. And this is figure of result. X-axis indicate count of workers in the log scale, and Y-axis indicate win rate. We are 1000 game played. Red line is our method's improvement. With one worker, the win rate was not even reaching half because the syncing time penalty. But our method scaled reasonably at least up 60 workers, and 60 workers achieved 65% won. For comparison, the win rate of optimistic pondering by Hempstead shown as blue line. Optimistic line, called OP, is evaluated under the low-cost environment similar to us. Our method was slightly below, but considering time control differences, OP had a longer thinking time than our experiment. Commonly, short thinking time is more difficult to parallelization. Then I'm positive that we did a good fight. Now, we demonstrated an asynchronous parallel method, and it worked on LAN environment and short-time match loop. Furthermore, this method is only needed the expert records and small changes from a sequential program. We hope that it is easy to apply for other games. For future work, we should improve the estimation method of realization probability, not only from rank information. And we want to learn on more practical environment. That's all. Thank you for your kind attention.
Any questions?
Yes, you compared your work to start to TDS AB, which is related by John Romain and David from Mark Rockington. They are mostly using transposition tables. Are you using a shared transposition table or local transposition tables? What would you use?
Well, we are not sharing transposition table, but very limited to this slide and this information from transposition table and sharing between client and master. But this size is very small. And
so the top 3 lines of the table are shared?
And yes, this is when only when tree growing, this information is sent. Then, when searching descent is when searching in descent is not sent.
The related question is what kind of network do you use? Because if you use a very slow network, then you can see that you cannot use a shared transposition table. So, is it 100 megabits, gigabits?
I expected 100 megabps RAM.
Okay, thank you.
For example, in university.
Any more questions?
But,
you change. You have improved the reading time figure. Previous, especially some second, a few seconds to for the preliminary search. Yeah, and so you have improved the short the time. Right.
GPS Shogi has 1 second preliminary search,
Right.
but my experiment is total time is 1 second.
Total of what?
Per fly,
Assign jobs all time
in this experiment, we exactly 950 millisecond to search, but 50 millisecond to penalty has reflect the cost of these growing tree and small data set and these operations.
1 second is fixed by you, designer. Yes.
Yes.
Yeah. So actually, only 15 milliseconds is used to compute several things and growth and master tree and so on.
Sorry, one more thing.
Yes, tree management is done within 50 milliseconds.
Oh, so very big improvement.
Yes.
Successful.
I believe.
questions? Actually, I have a question about how do you choose the probability of, you say you use Juoka algorithm? Juoka.
Tsuruka.
I'm just wondering what that is.
Tsuruka.
You use that to set as a guideline to choose something to do jobs. So I'm just wondering what that is. Probably we don't have that much time, so probably I can ask you later. Okay. Okay, after the talk. Anyways,